we should define that. So all atoms except for the noble gases have a measure of electronegativity. Those measures are right here on the board. There's numbers associated with every atom representing each atom's electronegativity. So what is electronegativity? You gotta get finished. Are you almost unzipping and unzipping and getting ready?
Yeah, I'm good.
Are you sure?
I think so.
Okay. That was like 8 zippers. It was crazy.
Oh, I was looking for something that wasn't there. I left
You
my
need
slides
anything?
out.
I got pens and stuff.
No, I printed out the slides, but I left them at home, so it's not really any use to me now.
That stinks. What's your name?
Marissa.
Huh?
Marissa.
Marissa, I don't mean to point you out or embarrass you, so don't.
No, it's alright. I'm sitting in the front, so it's
You
nice.
came in late, you opened the closed door, you walked all the way down front, you sat,
whole
you zipped,
2
you unzipped,
minutes.
now you're having a conversation with me, it's awesome.
It's good.
It's okay. This class should be fun. I don't know if you're enjoying it right now, but I am. And we should be open to discussions. I want you guys to participate in our story and conversation, so feel free. I teach at a pretty slow pace, only because I like it that way. Electronegativity, we're going to define that, and it's the tendency of an atom to attract a bonding pair of electrons. We should maybe write that down. I don't know if I can write that down. The tendency of an atom to attract a bonding, and that's a really important word in this definition, pair of electrons. So technically, an atom shouldn't really have an electronegativity because it doesn't really have it until it's in a covalent bond with another atom. But it's the tendency of an atom to attract those bonding pairs of electrons. In a sense, how prone is it to stealing an atom from an electron from another atom? You can see the periodic chart, which most of you are familiar with, that the electronegativity gets higher as you move to atoms with higher number of valence electrons. And it also gets higher as you move up and get to be smaller atoms. Now the reason it moves as you become more valence electrons is that those electrons are now capable of forming these bonds. They have a higher propensity to want to take an electron to fill their outer shell. The reason they get stronger as they get smaller is that the way they're taking those electrons are by using the positive charges in their nucleus. And as the atom gets smaller, those positive charges are closer to the other atom.
Say that again.
What?
Can you say that part again?
Are you recording?
Yeah.
That would be nice, and then the smallest electronegativity is down here. That's the atom that only has one electron in its outer shell. The atoms down here have 7 in their outer shell, looking to grab an 8, typically. These are your noble gases. They're already really happy. Their outer shell or orbital is completely filled. They exist as single atoms, and they're gases. They're not looking to form bonds with anyone. So as you get an an atom that wants desperately to become stable, that is, fill its outer shell, it actually has a higher propensity to steal an electron from someone else to do that. So that's why they get stronger as you move towards the right. You're filling a valence shell. It gets stronger as you move towards the top of the periodic table because those atoms are smaller. They have smaller atomic numbers. They have fewer electrons. And therefore their shells are closer to the nucleus where the positive charges are. And it's the positive charges that are going to attract electrons from other atoms. Right? Opposite charges will attract. So if an atom's going to try to steal an electron, it's going to do it using the positive charges in its nucleus. Notice that if this is the atom of lowest electronegativity, then fluorine is the atom of highest electronegativity. It's given a electronegativity of 4. Don't worry about getting stuck on all the numbers of electronegativities. What you need to understand is whether they're a big number or a small number, and is there a big difference between the electronegativities of bonded atoms. That's really what's going to be important for us to understand. And we have just a couple of rules. One is that if the difference in electronegativity between two atoms is greater than 1.7, the bond between them is ionic. So let's look at an example. Sodium and chloride, let's see. Table salt. Sodium is there, chloride's over here. Chlorine has an electronegativity of 3, and sodium has an electronegativity of 0.9. The difference between those two is 2.1. Sodium chloride is an ionic bond. Pretty strong ionic bond. If you think about table salt at home, it's a solid. Right? Those crystals are made up of sodium chloride, but the sodium and chloride are not covalently bound. They're held together by ion bonds. Right. The chlorine will have a negative charge. And why does it have a negative charge? Well, it's because it's stolen an electron from sodium. That difference was so strong that they're not even sharing those electrons anymore. Chlorine has stolen one. That's why it's an ionic bond. Yeah. Whereas you look at something else, let's say a carbon-hydrogen bond. Carbon, the electronegativity is 2.5. Hydrogen is 2.1. So the difference between those is 0.4. That's definitely less than 1.7. In fact, we're going to adopt the second rule. So this is rule number 1. Rule number 2 is if the difference in electronegativity is 0.4 or less, we're going to call that a nonpolar bond, where those electrons are shared essentially equally. This is going to become important to us, very, very important. So let's think about water again. I'll draw it a little bigger this time. Well, I wrote the electronegativities down here in case I forgot. Oxygen is 3.5 and hydrogen is 2.1. Well, my math says the difference there is 1.4. That's less than 1.7, so it's not ionic, but it's way more than 0.4, which is the nonpolar, equally shared bond. It's a very polar bond. That is, those electrons that sit between hydrogen and oxygen are way down here by the oxygen most of the time, on average. Okay, we all know electrons float around the nucleus, but on average, those electrons are very close to oxygen on both of those bonds because they're identical. That extra electron, and I'll circle it in red, indicating that it came from hydrogen. this one. And I'll give it this one. Doesn't matter, I can choose either one. That means that the positive charge in the nucleus of hydrogen is not particularly well balanced by the negative electron because it's not even close to it anymore. And that tends to give that hydrogen a positive charge, a partial positive charge. And this delta symbol means partial. Oh, be nice if I could spell. Same is true over here. If hydrogen's electron is spending most of its time near oxygen, that leaves that proton out there with its positive charge kind of by itself on average, and that hydrogen adopts a partial positive charge. Now, oxygen has 2 more electrons hovering around its nucleus than it should have on average. And so it adopts a negative charge, and the negative charge is exactly opposed to the bond between hydrogen and oxygen. And that means there's a partial negative charge here on the oxygen, and the same is true here. So I'm following this bond to the other side of oxygen and putting that partial negative charge there. So this is what water looks like if you could feel it. Feel its electric potential. It's very polarized. That is, one side of the molecule has one charge, and the other side of the molecule has a completely other charge. So the oxygen has this negative charge on it, and the hydrogens have the positive charge. And that makes the molecule polar, and certainly these bonds are polar. It's a polar covalent bond. And I'll put the letter S there because then I'm going to draw my arrow to the other one as well. Those partial charges on water are absolutely critical to its ability to do things. Otherwise, it would be like a noble gas, just floating around, incapable of interacting with other molecules. I think this is a movie, so let me see if I can start this. Let's see, how do I do that? This is a movie of water, a modeled movie, obviously, in which we're looking at just a bottle of water floating around. And you can see that the dark blue circles, those are oxygens, and the light blue circles are hydrogens, and the gold bonds are hydrogen bonds. Let me go back one slide. If I have a water molecule now with these partial charges on it, I need a smaller pen. I'm just going to put a little plus there instead of the partial sign. It takes up too much room. Put a negative here and a negative here. Well, that's a charged molecule. Well, what if I got another one over here with a partial positive charge on these and partial negative charge here? These things are floating around in solution and they're going to collide with one another. Well, if they come close to one another in this orientation, the negative charge on this oxygen can form an electrostatic interaction with the positive charge on the hydrogen. Remember, opposite charges will attract. The same thing is true over here. I'll circle the charge so as to distinguish it from the actual electrostatic interaction, which I'm representing by these dashed lines. By the same argument, I could put another water molecule down here. If I oriented it properly, I could have another electrostatic interaction here. And of course, I could have another one here. And all of these water molecules are likely charged, capable of interacting with other water molecules. In fact, each water molecule, the one I've got highlighted in green here, is capable of interacting with 4 other water molecules. 1, 2, 3, and 4. And the red ones are likewise capable of interacting with 4 water molecules in total. These hydrogen bonds we already understand are weak, about a kcal per mole. So they break and they reform all the time. And that's how we get to this structure of water in solution, where these hydrogen bonds are in fact forming and breaking. So you'll see maybe some of those gold bars dissolve and break and reform with other water molecules all the time. But this is the environment of the cell in terms of what water is doing. And it actually is pretty well structured. It forms like a cage inside of the cell. Lots and lots of water molecules all interacting with one another. If you ever took a glass of water and tipped it ever so slowly, trying to get out one water molecule, but you've never been able to do that. Have you? Nobody ever tried that? Pour until like one molecule comes out? I do it all the time. I've never gotten one to come out. It'd be hard to see because it's super tiny, but the fact is you can watch the water come over the edge and it just sits on the edge and builds up in mass until it finally starts to drip over the edge. And then it'll start falling off the edge, dangling in the air for a little while before it finally snaps free of the rest of the water and falls down in a droplet. And the reason you can't pour off a molecule of water is because they're all attached to one another through these hydrogen bonds. Try to pour off one water molecule and it pulls 4 other water molecules with it, and those 4 are each pulling 4. How many is that? Like 16. And those 16 are pulling 4. That's 64. And I don't know what 6 times 64 times 64 is. 256. 1,000, 4,000, 16,000, 64,000. There's about 1 billion water molecules in each drop of water. And the reason why it becomes a drop eventually is because the mass of that drop is finally heavy enough to break all the hydrogen bonds that are holding it to the rest of the glass of water. And that's how you get that drop coming off. So these hydrogen bonds, you think they're weak, and they are, but there's so many of them. It's like zipping up your coat, you know. One zip doesn't do much in a breezy day, but if you did it all the way up, your coat's not going to open, right? Nobody can come up there and tear your jacket open because each one of those zipper teeth is weak, but all of them together are quite strong. The straw that broke the camel's back, you ever hear that one? Or that's the straw that, what is that again? That's the final straw. I don't know even what that one means. But I know that if you hold one piece of straw and try to break it, it's easy to break. But if you'll have a whole bale of hay, boy, that's hard to break, or whatever it's saying. But anyway, you get the idea. Hydrogen bonds. And why is that important, you ask? Well, because this is the recurring theme, this polarity and the ability of the partial charges on these polar bonds to interact with other atoms is prevalent throughout biology. And it's certainly true of all of the interactions that occur within a protein. So we'll start thinking about that. So general structure of amino acid, I don't need to tell you this because I saw it was on your exam. The way I remember it is, and I only remember it this way since coming here, is that it spells out Naugatuck Community College. That's how I always start my amino acids. I know that this is the alpha carbon because it's the first one from Naugatuck. And I know that this is an amine group. And so I know amine groups have hydrogens on them. So I can plug those in. That becomes easy. And then I know that this alpha carbon has some weird R group on it. But I know the other group on it, the other atom on it is a simple hydrogen, and it's true for all amino acids. And then because it's called an acid, I know that there must be an acid group over here. And it turns out it's a carboxylic acid. That's the basic structure of an amino acid, right? And you know why they call it amino acids, right? It's amino and it's acid. Pretty straightforward. I don't know. Everything's simple, right? The only thing that's going to ever change for us is the identity of this R group. So that's easy. I ask you to draw the general structure of an amino acid. You got it. Okay, good. That's easy. So then we can start thinking about each individual amino acid. And this was originally an animated slide, but I'll draw on it as if it's not. We just drew out the amino acid structure, and so here's the amine group, there's the nitrogen and the two hydrogens on it. Anywhere there's not an atom, we're going to infer that there's a carbon. Okay? And then if we go take a look at this amino acid, and this is the simplest of all amino acids, we should recognize that. The side group is a hydrogen. Okay? This is not one of the amino acids you need to remember because it's too simple for you. Well, this is glycine. But they all have the same structure except the identity of this group. So we can look at them as a whole and examine the polarity of their covalent bonds. And that will inform us about things that they're capable then of doing. If we looked at the electronegativity of nitrogen, it's 3, and of hydrogen, it's 2.1. So these polar bonds here and here, these covalent bonds here and here, they are in fact polar. They're weakly polar. Remember, nonpolar is 0.4 or less, bless you, and ionic is 1.7 or greater. So that's a pretty big range between 0.5 and 1.6. That's a polar bond. The higher the number, the closer those electrons are to one atom versus the other. Okay? So these nitrogen-hydrogen bonds are in fact polar, and that gives them a partial charge. And I've indicated partial positive charge with a green circle and partial negative charge with a red circle in this case. The carbon-nitrogen bond, well, nitrogen is 3 and carbon is 2.5, so that difference is 0.5. And that's so weakly polar, that's essentially nonpolar. Okay, it's 0.5. We said polar was 0.4 or less. So, yeah, okay, it's polar, but it's weak polar bond. What about the carbon-hydrogen bonds? We've already measured those in the first slides. 2.5 minus 2.1, that's 0.4, and therefore non-polar. There's no charge on carbon, there's no partial charge on the hydrogen. Same thing is true for this bond. Carbon-carbon, by definition, if you have two atoms that are the same atom bonded to one another, it must be nonpolar because the difference in electronegativities will be 0. So that's certainly a nonpolar bond here. Carbon-oxygen, 3.5 minus 2.5, that's a polar bond, and therefore partial charges are indicated on it. The carbon-oxygen, 3.5 minus 2.5, 1, that's a polar bond. Oxygen and hydrogen, we've already looked at that for water. It's still very polar, just like it was with water, and so we put circles on them. And so if you look at this diagram and look at the sizes and the colors of the circles that I've drawn next to them, that's an indication of the partial charges that are present on those atoms. Okay, so this oxygen actually carries significant negative charge. Right? hydrogen positive charge. So this is a molecule that looks like it could form interactions with itself, but certainly could also form interactions with water, yes? I mean, the way I've drawn water before was that any partial negative charge on an atom could in fact interact with the partial positive charge on the hydrogen of a neighboring water molecule. And therefore there's a potential for a hydrogen bond there. Potential for a hydrogen bond here. Potential for a hydrogen bond here if we just turn the water molecule around. Right? So this amino acid is going to really enjoy being in water for the most part. It's going to be soluble in water. Its structure is going to be stabilized by water. Not all of it. This whole area here, well, not including that carbon really, this whole area here is nonpolar. There's no partial charges there to interact with water. So, but that's a small portion of the molecule. I sometimes throw in these review slides just to say, hey, look, we've talked about it. It seems like it happened quickly, but we've talked about some pretty important stuff. And we should make sure that we've appreciated what we thought about. And that is that, water is everywhere. Inside the cell, it's absolutely everywhere. It's polar. Every bond in it is polar. Every atom on it has a charge. And that allows it to interact with itself in this, forming this cage-like structure in the cell where it's forming and dissolving hydrogen bonds all the time. And it's capable of interacting with lots of other molecules in the cell too, including, it appears, at least amino acids. We're going to look at proteins soon, but since amino acids are the building blocks of proteins, it seems important that we consider them first.